Okay, so let's just get into it so we can say something before lunch. What I'm going to be talking about is an issue that was raised earlier on when we were talking about the which was the question of, well, I have functions now, do I have some sort of polymorphism automatically, right? And so we looked at the example of, right, the identity function, and there's a question of what is the type of the identity function, because hypothetically you could pass anything in and you get the same sort of thing out. And I was being a bit implicit about types, which is to say I had expressions that were untyped, they were just expressions, and then afterwards I said, oh, types are descriptors of expressions, but if we're using this style of types being part of expressions, right, which is I don't even have something unless I know what type it is, that's a prerequisite of even being able to talk about something, then it becomes a little bit more clear that, well, really what I have is a bunch of different identity functions, one for each type, right? So, for example, I could have the identity for Booleans, which would be lambda x of type bool, and then I return x. And what's the type of that? That's a function from bool to bool. What else? I could have id num, which is a function which takes a lambda x, which has type num, and I give back x, and that has type num to num, right? And I also wrote id alpha, which was lambda x of type alpha x, which has type alpha arrow alpha. And so the reading of, well, so each of these are different functions, and that's really the same darn thing, right? This annotation on the variable for a function, saying x is a bool, is more like help for the type checker. It has nothing to do with what that function does. It's just I'm saying what I'm going to let the input to. But because of this fact, this is a function of this type, bool to bool. This other thing is a function from num to num. The fact that they happen to behave the same way, modulo the fact that I pass in two different types of things, is not really something that I can say in the system, right? So you end up having to repeat yourself and define a different identity function or other functions for every type, and that's really redundant and kind of pointless, right? And even here, you shouldn't, and when I had alpha before in the simply typed Lambda-Calculus, which I talked about last afternoon or last morning, the alpha shouldn't be read like in standard ML or Haskell. This isn't polymorphic. This just stands in for some sort of primitive type, like think I've got maybe floating points in my computer. Alpha might stand for floating points. That's not the same thing as a Boolean, right? There's no unification or any sort of matching going on, right? That's just a different type. But this is really redundant, and no one wants to program this way, right? Really what you want to say is fine. Okay, fine, technically they're all different functions, but really they're the same function. I can just use it at a bunch of different types, right? So really what I would like to say is, what is the identity function? What is the identity function? Which is, I'm not sure yet, but it should have a type that is like for alpha arrow alpha. And what's that mean? That means you can pick whatever type you want for alpha, and it will be the identity function for that type. Okay, question? Yes. No, so it's not the same, right? So if I say this in the simply typed Lambda-Calculus, and I could also do the same thing and have beta arrow beta, right? in the simply typed lambda calculus, those are different types. They have nothing to do with one another. Yes, but the simply typed lambda calculus doesn't know that. So you can't unify. So there's a little bit difference of what the for all is, right? So functional languages have this really nifty, concise convention, but that's different from what the theory of languages is, right? So when you say this, it's not that, well, you know, that means they could be the same, but, well, not really, because maybe I instantiate alpha and beta so that they're different, right? And therefore, I don't know that those are necessarily the same thing once I've plugged in alpha and beta with their real types. And I think what you're saying, which is what we'll get to on Sunday, that it should be a fact that if a term had that type or that type, it would have to be the same thing. But you don't know that yet. That's an interesting property. Lambda calculus, we will never actually plug in bool for alpha. It stands for some constant type, right? Some sort of type that I have, but I haven't said anything about it yet, right? I have floating point numbers, but I don't know what they are, right? Because floating point numbers are weird. Another question?
I think it's actually the same question.
Yeah.
Variable, right, as a type variable, but like we're not, I mean, you know, any type would be a substitution instance of alpha, right? Because alpha is a variable. Except we're not there yet, and
we're not there yet, right. In a sense.
Quantifiers in order to be. Is that what
pretty much, and sort of the way you would talk about it in the simply typed lambda calculus. Well, you need a base case for types, right? The only type you have is an arrow type, something arrow something else, and I need a base case to actually write something down. And so, you know, when you were writing the simply typed lambda calculus, you could say, fine, all right, I have bool, I guess. That's at least something, right? And you'd say, my types are either bool or a function between things. That's something. But you might say, fine, I don't care what my base cases are. Pick some amount of base cases, whatever they are. Maybe they're bool and num and string and your favorite other stuff. That part doesn't matter. What I'm talking about is the functions. Right? So in the lambda calculus, we're only talking about functions, and we don't care what the actual data that we're manipulating is. So that level of polymorphism of I don't care what these types alpha and beta mean is at this very meta level, which is you could instantiate the simply typed lambda calculus with simply typed lambda calculus plus strings and numbers and floating points, and that would be a language. Right? But we're not sort of, that part doesn't matter, right? But that's not within the language. I want to say, I've got a program which could work with every type, right? So the simply typed lambda calculus doesn't talk about that. It just says, what primitives does your operating system support? Something you can be polymorphic in the language, right? We don't have well, let's suppose I also have some sort of primitive support for some weird fancy thing. Right? I don't know, right? It depends on my machine. In some sense, the language description of ML and Haskell and these other languages, they don't care what's on your operating system, but within your language, you don't quantify over your operating system. Right? So that's at a different level than I wrote a program that in the language doesn't care. Right? And that's the difference. And so we're going to be talking about how do I add a for all quantifier into the language so that I can say, here's a program that does indeed work with all sorts of types. And that it doesn't matter to it. It never needs that fact. And so we kind of want to embed this reasoning into the language and then use it for something. Okay? So that's the idea. And that's kind of that shift from these are base types that are there, and I'm not going to say what they are, to really, these are type variables that will start instantiating with stuff. Right? That's the big shift here. Okay? Sometimes people call these atomic types. Right? They're somehow the atoms and they're arbitrary, like I have an alphabet of letters. I don't care what those letters are. But now we want to quantify over those things inside the language. Okay? So I'll look at a system that is called SystemF. Or the polymorphic Lambda-Calculus. depending on who you're talking to. So it has two names because it's so good it was invented twice. So first was Girard, who's a logician. And so he really cared about the logic aspect of it. But he came up with this representation called SystemF that was about the for all quantifier, if we think of this as a logical sort of thing, right? Like for all numbers, that number is either even or odd, that kind of thing, more or less, but at a more high level. And then over here we had a computer scientist, Reynolds, who really wanted to talk about programs and running programs and this sort of practical application of I want abstractions in a programming language, which for the time was, pretty advanced. That wasn't something people were really doing. So that's the system, and it's really small. So I'll give kind of the whole thing and skip over the redundant parts that we've seen before. But really, it is just Lambda-Calculus plus something for all, and that's it. Okay, so let's first look at the types, because that's really the meat of it, is the types. So here, so let's see. So first I'll give the very detailed abstract syntax and then the pretty one, right? So we had originally some sort of alpha in the simply arrow type between tau 1 and tau 2, and then I've written it like alpha, and then the arrow I just wrote as an arrow, tau 1, 2, tau 2. So I said that was the types of the simply typed Lambda-Calculus. Really all we've got is arrows. And so how do we add this? Well, let's just add an extra type, the for all, which, what's the point of the for all? What's its role is to quantify over a type variable, which is like the lambda quantified over a value variable, or a variable of some sort of expression. It's the same sort of thing. It's just a binder. What it's binding is one of these alpha guys and inside of another type. And then the pretty way to write that, of course, is with the upside down A character, which is a standard way of writing for all. So two ways of writing the exact same thing. And so that is the extra addition for polymorphism. So in types, not that much you have to do. Are there any questions about what I mean here? Yeah?
The tau, do we expect it to be arrow type or any type?
So that could be either. It's any of these types. So this could be an alpha, an arrow, or another for all. So there's no restriction of what tau could be. It's anything I could write down. Yeah. Question? Other question?
So we have no free variables in types.
Well, so that's an interesting thing, right? You could have free variables, but you don't have to, right? You could have closed types now.
Closed types mean the only variables are bound.
All the variables are bound. So, for example, what's a closed type? So I could say alpha, well, I wrote them here, right? So now here, this is a free for, right? You have to be careful about the binder. And free variables, really, it's the exact same thing. And so here, this is a type with the free variable alpha in it because it's not underneath a binder. But here, there's no free variables, right? We've captured it with a for all, right? It's now bound by that for all. So the for all lets you then limit the scope of these free variables rather than being quantified at the very, very most top level of your programming language. Yeah.
What's the difference between an unknown, a name of something that's unknown, and a variable?
There isn't that much difference, which is kind of the interesting the interesting theorem of the SystemF, right? Is essentially the fact that you're doing something, the fact that you can do something without knowing anything about it means that you work with everything. So to say that I work for, yeah, exactly. So I work for a specific alpha, but alpha has no definition, ends up being, and that's, you kind of see that in the typing rules, right? And when we get to the typing rules, we'll sort of see there's an extra step of being pedantic where we talk about where it's bound, and essentially the spilling out some free references that, okay, maybe I put in a reference to floating point numbers that I don't even define any operations for them. Then can I quantify over them? But there is a limitation, right? So I could say, I've got floating point numbers. I don't tell you exactly what the constants, values, and eliminators are, but I'm going to assume I've got a big standard library that defines a bunch of operations on them, like addition and minus. You can't quantify over that because, right, you can't sort of swap out and say I use this operation for floating point numbers. It comes in from my operating system and processor, but somehow I work for all possible things. No, that's different, right? You've used an operation that someone else had already made the choice for, right? So we'll kind of see how this, it's a little bit pedantic, but it's sort of an important issue to actually keep type safety, right? We still want type safety, and so how do we do that? Okay, so that's the types. So let's look at the expressions. So what are the expressions? So this one isn't that great. So let's look at the the simply typed first, the simply typed lambda calculus first. See what, remember what we had. So here it was just, this is also very light. Here, there we go. Remember here we had variables, right? There's only three things: a variable, a lambda, right? Lam, and if we want to be very careful about the type there, we could say what the type of its parameter is, and then that was x.e, right? So we bind a variable on top of an expression, and then we also had an application, which was to expressions E1, the function, applied to E2, the argument. Okay? And we wrote that with the more common pretty syntax like this, right? So lam is just a lambda, where you say x colon t, and with a space. Was E1 applied to E2. Okay, so that was what we had. Calculus. And so, like for the arrow types, for function types, we had a way to introduce a function, a lambda, and a way to use a function, which is application. So we should do the same thing for all, or maybe should we, right? Really, there's kind of a couple ways to do it. You could just say, well, for alls is kind of this property of a term that already exists, and I don't say anything for it, it just happens to work. But here we're being very explicit about the type. I'm saying what the type is. So if I want to say it works for any type, I kind of need to say where I'm making that quantification. So in SystemF and the Polymorphic Lambda-Calculus, which are the same thing, you actually explicitly say when I'm using polymorphism inside of my program. And so how do we do that? Well, we do that maybe surprisingly or unsurprisingly, or cleverly or uncleverly, depending on your particular mood at the time, in exactly the same way. As a function, it just happens to be a type instead, which is either very surprising or very boring. So in addition to function lambdas, for all lambdas and for all applications, which I'll write with capital letters instead, as is the tradition. So big lam looks like a function, except the variable that you bind stands for a type rather than a value. So what's the application got to be? They have to somehow have something to do with each other. What is application? So the application form provides a type to one of these things. So capital app is E1, or just E, applied to some tau. I'll write it like that. So what's this saying? So this one is, I'm saying I've got polymorphism, right? That E works just fine no matter what you pick for alpha, right? So that's when I write a function in a functional programming language, and it's very generic, and so the language says, oh, that's okay, alpha could be anything. It doesn't really matter, so that's the quantification part. Here is an explicit instantiation, which says, fine, you've got a generic sort of thing. I've got a generic identity function, but now I want to use it at bools. So instead of that just implicitly working, well, because of course I could instantiate it, you're saying here, that generic type with this very specific type. So we're just giving a voice to what happens implicitly when you use a functional programming language. Yeah?
So what happens to x and e2 in the case?
X and 2?
Yeah. So do we first apply the type specification to that lambda, and then we apply that big lambda to the smaller lambda?
So right now I'm just showing syntax. That's all that is. Right? So syntax doesn't do anything, and in general, thing until I give it meaning. Right? So this is just a way of writing a bunch of stuff which means nothing. And then we'll get to how do you imbue this syntax with a meaning. And then we'll see where kind of things are connected. But before we get there, the preview is that when you apply a lambda, you plug in the argument E2 for x. When you instantiate polymorphism, you plug in tau for alpha. Right? So mechanically they look identical, which is maybe the surprising part. And then the pretty syntax is, so big lambda you write as a big lambda, typically. Sometimes people use the same thing, but that's just capital lambda is what that is. Capital lambda, E, and then the application instantiation I'll just write as E applied to tau, or E instantiated at tau. But yeah, so again, the two different syntaxes. Okay, so that's just syntax. So we should actually start to say what these things do, or what these things mean, for it to be interesting. And, well, especially since this is about types, we should probably start with the static semantics. So how do you check the types, or when are things typed? And so here a kind of interesting thing comes up. Right before we had that hypothetical judgment thing, right? And we're going to have to generalize a bit. So first we're going to have to take our existing hypothetical judgment and make it more general. And we're also going to have to use another form of judgment. And so to make this very explicit, so this is an issue that I don't think was raised yet. But really, a judgment is syntax, right? In programming languages, you're just dealing with layers on layers of syntax. So judgment is a collection of other things that are syntactic objects. And just like these expressions don't mean anything until I say what it is. It's the same thing for judgments. So the meaning of judgments will be defined by the inference rules we write in a type system. And we use suggestive names. That application, I hope to mean something like application. I could make it something else, and there's nothing wrong with that except that it's completely tasteless. But right, so suggestive names are helpful, but really the meat of it is in these definitions. So what are the two forms of judgment? So originally we had gamma, a turnstile, and then an expression, and a type tau. Okay, so that was the only really kind of typing judgment we had. That the meaning what we intend this to mean is an expression has a type tau. Expression E has a type tau, assuming that the free variables in E have the types ascribed by gamma. Right. So gamma, what's gamma look like? This is a list of x1 of type tau, ... xn of type tau n, right? So different variables, different types, with the side condition that each variable, there's no overlapping variables. Okay? So that's what we meant here, and this is just a piece of syntax so far. There's two things. So there's one. So two extensions. The first one is we've actually got free variables and scope in types now, right? So that's an issue because we have to keep track of where things are bound in order to make sure it even makes sense to talk about. So previously, types were really basic. We started with just num and bool. Clearly, those make sense. And then we said, OK, well, on top of that, I could add products and sums. And sort of inductively, that all makes sense no matter what you do. But here, you could run into issues where things don't really make sense anymore because there's binders. In the same way that with functions, right, or even just with multiple different types, I could write expressions that don't make sense because I'm adding numbers and booleans or something like that. You kind of get the same sort of issue where I could write down types, or inside the judgments, I need some properties about types that are no longer just trivial. I built it with some constructors, type constructors. So one of the extra judgments I'm going to write is theta entails that tau is a type. So that's the way I'll write it. So often saying that something is a type is written with colon star. That's the kind of types. And theta is just going to be a list of type variables. So so the meaning I would like for this is that tau is a type which may have free variables in theta but no others. Okay, so the property I want to hold is that the actual free variables of tau is a subset of what I'm listing in theta. Right, so I need to know, when talking about types, what references it might actually make, right? Or what sort of abstract types are still around in it. Okay? And so that's the first detail. That you need to also know this when you're checking the type of an expression. So in addition to knowing what are the types of the free value variables in an expression, I also need to know what are the free type variables in the type tau, right? What's generic in tau, what's generic in gamma, and even what's generic in E itself, because types now really appear in programs, right? They're not even just, I'm describing the type of an input variable, but I'm describing what instantiations are. So just like you want to keep track of what your free variables are for values, you also want to keep track of this free type variables. All right, question?
But theta doesn't have any information about like expression level variables.
No, so I'm keeping them separate.
Right.
So sometimes you might mix them up. It's pretty common to keep these separate.
Sure.
And you can get rid of this, but you'll kind of have goofy side conditions that say that directly,
Sure.
right? So we're kind of, rather than having this property that you calculate about all of the expressions and types you're dealing with, I'm including that inside of a judgment, and then we get to decide that by deriving some tree with some inference rules with that judgment, and then that's going to be tied together with type checking terms. Okay, so now let's go on to the typing rules, and we'll start with the part that has to do with the simply typed Lambda-Calculus, and that doesn't really change much. Well, no. Let's first look at the really new kind of judgment, right? Which is, how can we put a limit on the amount of free type variables you're allowed to have on a type? So let's calculate the type variables in a type using this judgment. So first, we've got basically we just have to look at each of those cases for types, right? There's only 3, so we just have the 3 rules. So if my type is the type variable alpha, what do I need to know, or what do I find out? Well, the free variables include alpha. right? Clearly, that's the base definition. The free variables of a variable is itself. So we'll say that. That is a well-formed type, assuming that I've got an alpha in scope, that I'm allowed to talk about alpha in my scope. I'll also say, kind of like variables, that maybe there's other stuff, right? I said it's a subset. I didn't say it has to be strictly equal to. It's just what you're allowed to have, right? So this is, I'm allowed to use the type alpha because I'm allowed to have alpha in my scope. Okay, so that's one rule. We've got an arrow type, so what's that look like? So an arrow type looks like tau 1, arrow tau 2. That, so arrows like pairs and all sorts of other constructors, that doesn't do anything interesting with bindings, so it's the same. Yeah, question?
So you said the theta can have more than
Yes.
three variables.
Right, so
What is that additional things? Are they like,
variables you are allowed to use, but you don't.
sorry?
Variables you are allowed to use, but that you don't use. The same thing here. The are a subset of really the domain of gamma, but right. So that's in the base case for variables, right? Might have other stuff, I'm not using it. So it's the same thing.
Example of that?
Here. So I'm allowed to use theta and alpha. I'm only using alpha. This is exactly the same as when you're dealing with terms, right? When we said gamma, right? This was always the rule for variables in every language we've looked at. Right? We said this, and we said, okay, sure, yes, it is the case that, if x is in scope and it has type tau, then x has type tau. There's all this other stuff I'm not using. Maybe. That's fine. Same thing here. That's the reason why it's greater, right? This is the case that does it, and then every other case inherits that property, right? If I were to say this, I'm only allowed to use an x if that's the only thing I have, then they would be equal. Yeah, that's the difference. Yeah, question?
The one that you wrote there, you're going to say that tau 1 and tau 2
Sir.
are
What? Yeah. So I didn't finish. I kind of got it. So that's not complete. Yeah. So So that's that bogus. Let's finish it. So what's the premise? And basically, it's that the scope of tau 1 and tau 2 are the scope of the arrow type of both, right? So there's no binding going on there. That's really what this is saying. The arrow does not bind anything. So, okay, we've got theta tau 1 and theta tau 2. Okay, so the variables that are free in this are just the variables that are free in both of them. Okay? And then the last one is for all, and that's the interesting one. So in some sense, if this is all you have, it's not very interesting. But the for all actually does something. So what about when I've got a for all? Okay, so if I see, when is it the case that for all alpha dot tau is a well-formed type, assuming I'm allowed to use the free variables in theta. And so tau gets to see theta, of course, but it also gets to use alpha. I'm adding this extra type variable to the scope of things I'm allowed to use, right? It's an extra generic type that for all introduces. So you say that the scope or the free variables of tau are now allowed to also, and assuming that down here the free variables of for all alpha dot t for sure won't include alpha because alpha is bound here, right? So it's safe to remove it from the environment theta because there's no possible way for there to be a free alpha in this type. because it could only appear in tau, and it gets bound right here, right? That's it's very much like lambda. It's pretty much the same thing. Yeah?
And we want to keep the bound variables of tau intersect theta. We want to keep that empty.
The bound variables of tau intersect. So we want the bound variable. Oh, the bound variables of tau.
Yeah, close parenthesis there, and then intersect.
I think that's the case. So that's not really my goal. It might be the case the way I've defined it. So really, it's I want to keep, in general, I want to thin out theta when I can, whenever I apply a type construction. You could hypothetically also have theta, but you're just muddying, or sorry, you can also have alpha still there, but you're muddying the waters. So there's no helpful aspect. And by the intuition, if this is what I really mean by that judgment, right? That's not the definition, but I want that to be a fact. And in fact, this is a theorem that you need to prove at some point, that if I have a derivation of this, this fact is true. I don't know that yet, because I've just said some stuff, but you want to prove that. And this is safe, right? You kind of want to do the best job you can while still not messing up the main properties you intend to capture by some syntactic rules. Right? I have an intended meaning in mind, and I want some syntax that decides yes or no for that meaning, or that defines or calculates it. Okay, so that's the type part. This is sort of the, question? Yes, there's also alpha equivalents for types. So really, everything that we talked about in expressions and in programs about alpha equivalent substitution bound variables is exactly the same thing in types. Really, types are just another set of expression-y things built from constructors. And those definitions are precisely the same kind of thing, right? There's no new information. Yeah? With these rules, the untyped variables? What do you mean by the untyped variables? So, alpha without a for all. So the only alphas without a for all have to appear in theta. Theta tells me what alphas might appear free without a for all that binds them. So that's what this means. The free variables of tau are exactly the alphas that aren't bound by some surrounding for all. There might be some of them, right, that there might not be empty. But whatever I have, I should say in theta. Theta is keeping track of what free variables I have in scope. Just like gamma keeps track of what free variables I have in scope in an expression. It's exactly the same sort of idea, right? You can, and that's different from for all alpha, alpha arrow alpha. They're different things. And I sort of alluded to that earlier. And then the question is, when can I introduce for alls and scope that off? And the system is going to tell you when you can do that. But the question of can I have them and when can I have them, right? This is my intended meaning. Actually, I have two of these, right? So really, I mean both of these things, right? So a term can have a type in it, right? We can say types inside of our programs. And so those might also reference theta. That's why it's kind of round. So the idea is that this captures the scope of variables that appear without binders in this thing. This captures the scope of variables that appear without matching binders in that thing. Right? Really, and maybe the surprising thing is the story is the same, right? Like everything we've learned about programs and the lambda calculus is starting to get repeated in one way or another in the type level. So the question of, is that how it works? The answer is yes, it works exactly like it does in programs. Yeah. Okay. Great. So we got that. So now let's look at the typing rules for programs. And I think we kind of, maybe let's continue on a little bit, because I feel like we're asking a lot of questions that is how will you do this? And I'm about to do those things. So let's finish a few more rules, and then we'll get into more questions about how exactly these things work. Because I kind of have to just wave my hand and be vague. So let's make a little bit more progress. So the rules for simply typed lambda calculus, right, were this. We had an application. So E1 applied to E2 has the type tau prime if E1 has the type tau arrow tau prime and E2 has the type tau. And then the abstraction part was I've got a lambda x of type tau dot E has type tau arrow tau prime. And type check that, I just add x to the free variables in scope, and then the result's got to be a tau prime. So these were the rules that we had for the simply typed lambda calculus. I'm just repeating them here. So how do we modify this? And the main thing, right, is that the theta keeps track of the free variables, free type variables in scope. Do any of these interact with type variables or mention them in any way whatsoever? Not really. There's no binders going on. I'm not making any new ones. So for these rules, you really just have the theta along for the ride. It doesn't really contribute much new information. It's just sort of saying nothing happens, see the sub-expression for what's going on. Right? So nothing's happening here. The interesting cases, of course, are with the new stuff that have to do with type abstraction and instantiation. Yep?
Do we ever need to have like common judgment that the tau is a valid type? Yes, like
yeah. So that's the one extra thing, right? So here you'd want to say something like, well, I'll get to that in 1 minute. So technically you can say this, but we'll sort of see where you want that rather than just do it. So in general, for now, nothing's happening, right? So so the abstraction and application of types looks like this. So the application form, the application form says, if I've got a generic thing, so what if E is some sort of generic program, right? E has type tau. Tau might talk about alpha, but it works for any alpha. The same E will have type tau for any choice of alpha. It doesn't really matter. It's up to you. And now that means it's up to us. We're using this thing, right? That's the application form. So that means I should provide the type I want to use it at, right? So here, gamma E applied to, well, I get to pick some tau prime of my choosing, whatever I want, right? So if this is for all alpha, alpha arrow alpha, I can say, I want to use you for Boolean arguments, and I would say Boolean here for tau prime. And what do I get? So what do I get out? What I get out is this, where my chosen tau prime is alpha, right? I want to put something in for alpha. How do we do that? That's just substitution, right? Just like when I write a function, right? What's the squaring function? The squaring function is x plus x for any x, right? The doubling function is x plus x for any x. Now I want to double 5. I plug in 5 for x. Entirely the same for what you do in programs as you do in types. There's no difference here. So you just say, all right, what you get back is a tau, where your chosen tau prime gets used for that generic alpha. And then so is that enough? So we should make sure that tau prime makes sense here. What does that mean? Tau prime makes sense was that stuff over there, right? That the variables are the type variables that you have.
Theta details tau is of type star.
Correct. Yeah, tau is a star. Or tau is a type is another way you can just read this is tau is a type with free type variables theta. So tau is indeed a type with free type variables theta. Okay, so now the abstraction part. What about that? For that one, right, I want to say, when is it okay? Abstract over some alpha, right? So what's the type of that? This is how I introduce polymorphism, which is to say this is how I introduce the for all. So this is going to be some sort of for all alpha dot tau. And how does that work? Right? Like, this is the tricky thing, but in some sense, this is the reason why we go through all of this riffraff about environments and scope and blah, 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 to make this easy. Right? Just like for a function, E works with any x, so I can abstract over it, right? It's not a particular x like 5. It really could be whatever you choose. And we say I can abstract over it by adding it to the environment. So x is a generic tau inside of E. It's not a specific tau in E. And so here, alpha must be generic in E and not a specific thing. Okay. Oh, and so how do we do that? You add that to theta. It's the same kind of mechanism as what we do for functions. Like, these really do look like functions. It just so happens that they're types that I'm passing around instead of values, with the big difference here that I learn something in the world of types when I instantiate. All right, and so like this is the tricky rule. If you don't go through all the riffraff of type variables, what is this saying? Well, if this makes sense, that means that the free type variables you see in both the expression and in the type cannot include alpha, right? Because alpha isn't in theta, because I'm allowed to add it to it. It has to be some other thing, right? I can't re-add the same thing. So really, another way, and you might see this, as it's okay to be generic about alpha when no one else talks about alpha. If alpha is some sort of generic type variable that's unique to tau and E here, and nothing else in gamma talks about it, then that's okay, because alpha is getting bound here and here, but somehow the scope is leaving for gamma. And that's kind of the example that I gave, which is maybe I have an alpha which stands for floating point numbers, and I can call that generic as long as I'm not using floating point operations that link to machine instructions. If I then change my mind and say they're strings, then I've crashed my program, right? If I use something, some library functionality or some functionality that someone else is implementing that also talks about alpha, that means I'm not really generic. There's some shared information here. To say that it's generic means that alpha is an artifact of just something I'm in my own world, and so therefore it doesn't matter what anyone else is doing. I'm independent with respect to alpha, with respect to the rest of the program. Alpha is just my idea, and so I can abstract over it. So I think there were some questions, and we can start to get into those now. Yeah?
Just real quick, this rule on the top right, it's hard for me to see which taus are defined. You just make it darker.
Taus? Oh, yeah.
Prime stuff.
The primes are right here, and oops, I forgot the prime here. Those are the primes. Yeah. So the only tau was the thing in the for all and the thing I'm substituting for, and the primes are everything else. So were there some other questions? Yeah.
Just strictly syntax. Alpha is never a theta on the top, right? It's sort of like
Yes.
It's sort of like a syntax trigger to say that like alpha is somewhere in this context. You know?
Yes.
I'm not going to show you all the elements of theta because that would be annoying.
So
but-
exactly, and this is well, kind of also an thing. So this is a good related question, and I can't remember how in detail we got into like what is gamma and theta, right? So really, this one's a little bit simpler. Theta is a set, and so when you use this notation, theta comma alpha, the understanding of what people mean is theta is a set that does not contain alpha, and then I add alpha to it. So there's kind of this idea that we don't overlap existing things, right? So by the fact that I can add alpha to theta And that means something, it means alpha was not already in theta. And so that was when I said down here, alpha's not here. And it's the same kind of thing here, right? There's no shadowing in this presentation, which is to say, I don't already have X in scope, right? Because here it's not just, it's unordered, right? We don't care about the order. It's not a list of a particular sequence, really. This says that alpha appears anywhere over here. It's undefined what order it really is in, because that's a detail we don't care about. And same here in gamma, I don't care about what order you write this in. Those are all considered equal. But I shouldn't have X appear twice. I shouldn't say X is in scope and it has type bool, but also X is in scope and it has type num. That would be silly. How could it be both? Right, so X only, so that for each variable, it can only appear once in the environment gamma and have a particular type. But then, of course, you can use the same type multiple times, right? I can have X, Y, Z, and they're all numbers. That's no problem. But I can't have X, 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 and they're all, and they're different types. That would be silly. Or even the same type is pointless. But yeah, so question. Let's go back and forth. Question? So tau prime here does not have a alpha in it. And it doesn't need it because I'm replacing alpha. Tau prime doesn't really need to refer to alpha. And so there's kind of these renaming issues, right? And it's kind of like shadowing. So technically, the term lambda x doesn't directly type check because I would try to add X to my environment twice, which is not allowed. So I'd say, oh shoot, this doesn't type check, but it's a perfectly sensible thing. But that's okay. That is if you rename things, right? I could have well just said lambda x lambda y dot y. Same expression up to renaming stuff, but there's no shadowing problem. Right, so you should, in general, you might as well assume that the free variables that tau prime talks about are different from alpha. And there's no reason that it should have to talk about alpha. Right, this is sort of the case of, I've got my generic algorithm over lists of whatever alpha is, and I say, okay, I want to now work on fixed width integers. Right, fixed width integers doesn't have to say anything about that alpha. The alpha is an artifact of binding. Okay? Yep.
Is SystemF type safe?
Yes, SystemF is type safe.
Meaning there are no...
It's really the same kind of type safety theorem. The detail, right, is you want closed things, so both of them have to be empty. But aside from that, actually I'm not sure if that has to be empty, but you might as well say that.
So what about non-terminating?
So also it's terminating, and that's one of the things we'll be talking about on Sunday. Which, so SystemF, in one sense, is, well, it has all of the nice properties of the lambda calculus, more or less, right? So it's type safe, and you can't loop forever, things like that. But it's way, way, way more expressive than the simply typed lambda calculus, which is maybe surprising. Like, I introduced this as, I'm bored of writing basically the same code over and over. And that's useful and practical, but not really earth-shattering that I've saved typing a few characters. But it turns out you can write way more, it's more expressive in an essential sense. So there's more programs and more behaviors that I can represent in SystemF because of the quantifiers that you just can't do in simply typed lambda calculus. So one of the examples, as I said, you didn't really have recursion anymore. And the simply typed lambda calculus, you just really had function application, and it was a really fixed thing. But here, and that's what we'll get to after lunch, you can encode all sorts of interesting types. So, for example, Booleans, I showed how to encode in the untyped lambda calculus. You can actually ascribe a meaningful type to that, which is the right one, the one that you want, which is kind of interesting. But you can also encode numbers, which I had given as a fun puzzle exercise in the untyped lambda calculus. and those are still typable here. And the numbers come with that kind of recursor that we saw yesterday, right? So I can write primitive recursive things. It's also expressible here. So you can do some amount of recursion in SystemF by using these fancy encodings, but you have no opportunity of looping forever. And that was one of Gerard's, at least. So Reynolds was from a more practical point of view on how do we make good programming languages, but Gerard was from the more logical point of view. And one of his motivations for this was a dissatisfaction with essentially what I showed you is sometimes referred to as Gödel's system T, which is basically lambda calculus with numbers and a recursor, is the name for that. But the problem there is, fine, I've got functions and I've got numbers, but what if I want to talk about lists? I would have to add lists. And what if I want to talk about trees? I would have to add trees. And this is very boring. And I showed how with general recursive types, with a mu alpha dot tau type, you could encode all of them, but we've lost essential properties like termination. So what Gerard said is, I need termination, but I don't want to have to keep extending my language with every kind of thing I want to talk about. I want a very generic language that can talk about all sorts of things, but without losing termination. And so that's one of the uses of those encodings that we'll talk about in the afternoon, which is how did we sneak in numbers and booleans and pairs and sums in one form or another into this language super, super tiny. I don't have any of those things, but now I do. Right, so it's kind of recovering some of that power from the untyped lambda calculus. The type smashed away, and now it's boring. But you add type quantifiers, and now it's interesting again. So that's that's one of the things, right? So we're going to go through some of those encodings on how you can recover some of these basic types using for alls and functions. Okay. Any other questions? Yeah.
Back to my question just now that these rules does not require that tau to be closed, right? Like for both.
No.
The first rule for both x is that tau, but the tau may have variable that is not
Here? Oh, yeah. So getting back to that point, so thank you for reminding me. So that was one detail I do want to actually mention, which is I said that aspirationally I want this to be true, but it's not. So quick counterexample. Let's look at a counterexample. So x has type alpha, x has type alpha. Oops. Right? I meant to say that theta captures all the free variables in scope, and that's not the case. But really, this is the only problem case for what I've written down. And so the fix, and it's not too hard here, is you add an extra premise, which essentially just checks that indeed tau only refers to things in theta. So there's an extra premise here, which is annoying and kind of ugly, but not too bad right here. And you might go further. You might say, oh, not just theta, but everything in gamma. All right, so if I want to enrich this theorem to not just say that this bounds the scope of the type of the term, but also the type of all free variables in scope, then you would probably want to say more like this, that it captures the scope of the entire environment. And then I'd have some rules that say, in addition to all this, how do I extend this to gamma, which is just that. You're just breaking out a sequence. Empty environment, that's fine. And then an environment with something in it, right? If I've got gamma x dot tau, well, I should check that gamma's fine, and I should check that tau is fine. All right, and so here, I'm only allowed to actually use a variable as long as the theta matches. And I'm not kind of lying in that case. And assuming you've got that premise and those rules, then you actually have a theorem I said. Well, so it's not just that, but you want to say something like theorem if theta entails tau is a type, then the free variables of tau are a subset of theta. Also, if theta and gamma entails that E has a type tau is I can derive one of these things. So theta entails that tau has a type, and theta entails that gamma is a sensible environment. So that's something you'd want. So the first one is just that, yes, this judgment captures my intended meaning, but also if I type check a term, the type makes sense and the gamma environment makes sense with respect to the scope of theta. So that part in particular, you need this extra premise for the base case, and the rest of them just follow by induction. Yeah, so this isn't too bad. If you get into more advanced languages and logics, these extra sanity checking things become quite annoying. But at least here, it's kind of reasonable. Okay, so I'm going to wrap up here for lunch. We can address any other quick questions, but then I'll continue on and get more into SystemF and then talk about another type of quantifier when we get back. Okay, so are there any brief questions before we break for lunch? Yeah?
So we won't have type rules for big lambda and big because it will happen at compile time kind of thing?
The question is, we won't have type rules for big lambda?
Sorry, dynamic steps, semantics, like dynamic.
I'm going to talk about how to run them, but yeah, so there are rules for how do you evaluate an application of a big lambda.
So does that happen at like compile time kind of?
So that happens at runtime, but the property you get is erasure, which most good functional languages have, which says you can run a program with big lambdas in them, and I'll show you how to do that, and it's the same thing as functions really is the preview, but you can strip them all out, and then you have an untyped program, and that runs just as well. It gives you the same answer, right? So that's called erasure, which is, can I take an expression built this way? Yeah, and so I'll mention something about that afterwards. But yeah, great. So I think that's it for lunch. And
Typo there on
maybe.
the second line, it should be tau colon star. Or is tau
Second line. Oh, tau colon star. Thank you. Yes, that is a typo. Yep. Tau colon star. Okay. So I'll continue on after lunch.